Methane reacts with oxygen to form carbon dioxide and water. How many oxygen molecules are needed to react with 47 methane molecules? What mass of oxygen is needed to react with 24 grams of methane? And what mass of methane is needed to react with 3 moles of oxygen? This is a balanced equation for the reaction. When solving these kinds of problems, it's essential that you begin with a balanced equation. How can you know if an equation is balanced? Every atom that appears on the reactant's side, the left-hand side of the reaction, also appear on the product's side, the right-hand side. That means that every substance is accounted for before and after the reaction. Let's see that. There's that carbon atom before, and there it is after. Each hydrogen atom before and after, and each of the oxygen atoms as well, before and after the equation. That tells us that matter has neither been created or destroyed, which would have been impossible. That's what a balanced equation means. What do these little numbers here and these bigger numbers mean? The little numbers refer to how many atoms of that kind there are in one molecule. So here we have a methane molecule, and we can see there are 4 hydrogen atoms per methane molecule. Carbon actually has a little 1, but we don't write that because there's 1 carbon atom per methane molecule. The large 2 written in front of oxygen to balance it refers to 2 oxygen molecules. The small 2 subscripted refers to the 2 atoms of oxygen within 1 molecule. Now, these coefficients at the beginning is actually a 1 in front of methane and a 1 in front of carbon dioxide, although we normally leave them out, don't literally mean that only 1 methane molecule can react in this reaction and only 2 oxygen molecules. It's a ratio. What does a ratio mean? A ratio is a balance. The balance between methane and oxygen is 1 molecule for every 2 molecules, because unless there are double as many oxygen molecules around, the methane can't find the right number of partners so that it can form carbon dioxide and water. And so, for them to react fully, there always have to be double as many oxygen molecules as methane molecules which react in this particular equation. But any form of that, for example, 2 methane is to 4 oxygen, which would form 2 carbon dioxide and 4 water. That is the same ratio. Although obviously it's not the same numbers. 1 is not 2. 2 is not 4, but the ratio of 1 is to 2 is the same ratio as 2 is to 4, because in both cases the first thing mentioned is half the second thing mentioned. Now we can write this ratio of 1 methane molecule is to 2 oxygen molecules is to 1 carbon dioxide molecule is to 2 water molecules in infinite different ways. One of them is this here. 6,02 times 10 to the power 23 methane molecules is to 2 times that in oxygen molecules. Notice this is the same ratio. We still have double as many oxygen molecules as methane molecules. Although it's the same ratio, I'm not saying that 1 molecule equals 6,02 times 10 to the power 23 molecules. Of course they don't equal one another. But the ratios of 1 is to 2 and 6,02 times 10 to the power 23 is to 2 times 6,02 times 10 to the power 23. The ratios are the same as one another. Now, there are infinite different ways we could write that same ratio. This is only one of them, but this is a particularly useful one because we know that this group is equal to a mole. And so I can write this line in another form. They are both the same ratio, and actually they're exactly the same thing. 6 common or 2 times 10 to the power 23 molecules is 1 mole of molecules, and so on. So here we have the ratio. 1 mole is to 2 mole is to 1 mole is to 2 mole. It is the same ratio as the top, although 1 molecule does not equal 1 mole. Don't think that. But the ratio 1 mole is to 2 mole is the same ratio as 1 molecule is to 2 molecules. These that we've been referring to so far are particle reacting ratios. They refer to how many particles or how many groups of particles of each type react relative to one another. But what if we rather wanted to know what masses of each type react relative to one another? If we wanted to convert this into a mass reacting ratio, how do we do that? We ask ourselves, 1 mole of methane, what is its mass? 2 moles of oxygen, what would the mass of that be? And so on. And by this time you should know how to calculate that using the molar mass information from the periodic table. So you should now pause the video until you have this reacting ratio yourself. This is what you should have found. This particle reacting ratio, 1 mole methane is to 2 mole oxygen is to 1 mole carbon dioxide is to 2 mole water, is the same ratio as 18 grams methane is to 64 grams oxygen is to 44 grams carbon dioxide is to 36 grams water. It's just given in another form, in a mass reacting ratio form. So here we have particle reacting ratio in one of its simplest forms, and the mass reacting ratio in one of its many forms. The form written here is just an easy one to work with because 1 mole has a mass of 16 grams. But obviously we could have doubled all this, and we could have said 32 grams is to 128 grams is to 88 grams is to 72 grams. That's the same ratio, and there are many other forms in which we could have written it. So here are all the forms of the reacting ratio for this particular equation that we've gone through so far. Now we get to the questions. The first question asks how many oxygen molecules are needed to react with 47 methane molecules. Write that question down in an equation form. Pause until you have got that. This is what you should have written. How many oxygen molecules are formed from 47 methane molecules? What do you have to do next? Remember, with the unit factor method, we multiply that by a fraction such that the numerator and denominator are equivalent. What unit should we have at the bottom of the fraction so that we can remove the given information? What unit should be at the top of the fraction so that we can introduce the new information, and what values are equivalent for each of these units? Can you answer this yourself? Here are the reacting ratios. We need to identify which pieces of information within all of these ratios is relevant to this question. To do so, we ask ourselves, what is the given and what is the required information? Here we have the given information, methane molecules. And here we have the required information, oxygen molecules. So therefore, what is relevant within all of the reacting ratios we have? Number of methane molecules reacting with for every how many oxygen molecules? So now here we have again our question. How many oxygen molecules react with 47 methane molecules? And can you answer this now? What should the unit be of the factor that we multiply by the top and the bottom of that fraction? What should each one's unit be? And what values should we assign to each of those? Can you answer this yourself? Try to before I show the answer. We need to divide through by methane molecules to cancel out the given information's unit, and we need to multiply by the number of oxygen molecules to introduce the new unit of the question. But we have to now ask ourselves, well, how many oxygen molecules is equivalent to how many methane molecules, so that this multiplication is legal? And we get that from the reacting ratio. We know that every time one methane molecule reacts according to this equation, 2 oxygen molecules are required. So for this particular equation, 2 oxygen molecules and 1 methane molecule are equivalent in that they react with one another. And so we can find out the answer, 94 oxygen molecules. Notice we need double as many oxygen molecules as what we need methane molecules. And we've seen that all along. That's what we saw from the reacting ratios. Unless there are double as many oxygen molecules as methane molecules, not each of the atoms can find a partner, or there would be too many partners. So only if the ratio between methane and oxygen is 1:2, only then can the equation be balanced. And that is exactly what we found here. Our next question. What mass of oxygen is needed to react with 24 grams methane? Write this question in equation form. Pause the video until you've done this yourself. This is what you should have written. How many grams of oxygen are needed to react with 24 grams of methane? How do we answer this question? We need to multiply it by a factor such that the top and the bottom of that factor are equivalent to one another. But for this to be useful, we need the bottom of that factor to cancel out the given information. So what is that? We need the top of that factor to introduce the required information. So what is that? And then of course, the values must be equivalent so that the multiplication is legal. Can you already answer this yourself? Try. We know that we have all of these reacting ratios, and we need to decide which of them is relevant to this particular question. So we look at the required information, mass of oxygen, and the given information, mass of methane. And so mass of oxygen and mass of methane are relevant. We need to know what the reacting ratio in the form of mass methane, mass oxygen is, because that can help us solve questions about mass oxygen relative to mass methane. So now that we've identified which parts of the reacting ratios are relevant, we can solve our problem. Do this before you continue with the video. You should realize that we need to divide through by grams methane, and we need to multiply by grams oxygen. What value of each is equivalent to one another for this particular equation? Where do we get that from? From the reacting ratio. And we see that every time 16 grams of methane reacts, it needs 64 grams of oxygen. So these two values for this particular equation are equivalent to one another. And so we can divide one by the other and in effect get 1 and multiply 24 grams by it legally. And so we find our answer to be 96 grams of oxygen. The last question. What mass of methane is needed to react with 3 moles oxygen? Write this in the form of an equation. Pause until you've done it. What's the next step we do? Can you do this yourself? We need to identify the relevant parts of the reacting ratios. We look at the question. It refers to mass of methane, so we need to have mass of methane within the reacting ratio to help us to answer the question. It refers to moles oxygen, so we need to have information about moles oxygen in the reacting ratio to help us to answer this question. Now notice that 1 mole of methane has a mass of 16 grams. 2 moles of oxygen has a mass of 64 grams. So in fact, we could write the ratio 1 mole methane is to 2 moles oxygen as 16 grams methane is to 2 moles oxygen. Or we could write the ratio 16 grams is to 64 grams oxygen as 16 grams methane is to 2 moles oxygen. What's the next step we do? We need to multiply the question information by a factor. What should the units of this factor be to be useful? We need to be able to cancel away moles oxygen, the given information, and introduce the unit gram methane. What mass of methane in grams is equivalent to what number of moles of oxygen in this particular equation? Where do we get that from? We get it from the reacting ratios. We see that every time 16 grams of methane reacts, it needs 2 moles of oxygen to react with. So for this particular equation, 16 grams methane and 2 mole oxygen are equivalent values. Dividing one by the other, in effect, it gives us 1. And so we can multiply 3 by it, and that's legal. We do so, and we find our answer. 24 grams of methane are needed to react with 3 moles of oxygen.